connecting in any case. Okay.
Do you need to give some information or do we start straight away?
Muted, Enrico. I think the answer is no, but
yeah, no, I think we can start straight away, at least from my side. I don't know if Bene or Valentina have different opinions, but yeah.
Christian is there, is he? Do you want me to? I can't. Yeah. Should I wait for 2-3 minutes for people to connect?
Yeah, I would say let's wait maybe a couple of minutes. I mean, we were around 80 people connected yesterday, so
yeah,
I'm confident some people will come in soon.
So is it me or you're not sharing the screen yet, Christian?
Yeah, maybe
I'm not sharing it yet. I can start anytime.
Okay, then you can start maybe.
Yeah, that would be good.
Maybe while we wait, just a very quick reminder to all the speakers. If you have a move in your presentation, you can click, there is somewhere, I don't exactly remember where, this optimize for video streaming, which, or video sharing, which, yeah, will make the movie be smoother for everyone.
Sorry, on Slack, okay. No problem. Try to rearrange all of my windows so that I can see both hand raised and the question on Slack. All right. Okay, I think we can start. There are still a few people connecting, but I think we can start. Okay, so welcome to this second day of the SIP on the metals and dust. And we start this session with the invited presentation by Christian Plantor on the recent progress and outstanding issues in the emerging CGM. Please, Christian.
Good morning in my time zone, and thank you to Valentina and Bene and Enrico and everyone else who was involved in putting together this talk. I'm learning a ton. I miss being together with you in person, but it's wonderful that we have this platform where we can get together, at least virtually. I'll be talking with you about theoretical models of early metal enrichment and observational signatures thereof. I won't be talking so much about dust. That's not my wheelhouse, fortunately. Joe Lewis will be giving us a talk about that later on, so he can fill you in. A warning, it's been difficult for me to keep up with all the work that you've all been doing, especially since about fall of 2019. So if I omit something important, please bring it to my attention and I'll set the record straight going forwards. So let me start just by giving a little bit of physical context. Again, my talk is going to be rooted in the circumgalactic medium, which is what I'm most familiar with as an environment for tracing the enrichment of galaxies at early times. So I want to talk about the difference between the circumgalactic medium and the EOR and what it is just physically at lower redshifts where it's perhaps a little bit better studied. We can start by just looking at the properties of a 2 sigma peak in the density field and the sort of dark matter halo that generates at redshift of 2 versus redshift of 6. So a typical star-forming halo at redshift of 2 might be a group-sized halo, 10 to the 13 solar masses, maybe a little bit less. But at redshift of 6, that's not what you're looking at. A typical star-forming halo at redshift of 6 is going to be more like 10 to the 10 solar masses. So that by itself means that when you're looking at the circumgalactic medium where a lot of the baryons, actually most of the baryons and a lot of the metals are, you're looking at a very different environment just because of that. If you multiply the mean density by 200, just using spherical collapse, you find that the typical densities of the gas and the halos differ by more than a factor of 10 between redshift of 2 and redshift of 6. The virial temperatures are also different by more than a factor of 10. You're looking at colder halos at higher redshift, and that's going to have some implications for the ionization state of the gas that you're looking at. The ionizing backgrounds are different too. And of course, you'll get slightly different numbers here, depending on whether you're looking at Claude André's model or the Hart-Maddow model or someone else's. But roughly, you might expect to see something like a factor of 4 difference in the amplitude of the ionizing background. Here, that's quantified as the rate at which hydrogen atoms get ionized per second. So if you have a hydrogen atom that recombines instantly, it gets reionized with this frequency here. So a large number is an intense background and a small number is weak background. So you have about a factor of 4 more intense background at redshift of 2. That's before you account for local UVB fluctuations. The metallicity is expected to be larger at low redshift, less at high redshift. Exactly how much, it's something people are still trying to work out, but we had to talk about that yesterday, which emphasized this. So roughly speaking, typical star-forming halos during the EOR are going to be denser, colder, less irradiated, and less metal-rich compared to what they are just at redshift of 2. So even if you're looking at the same column density and the same ion, you're probably looking at a different kind of gas or a different portion of the halo at high redshift just because of these reasons here. One thing that I think is underemphasized in the literature, but people are starting to be able to account for it now, is the fact that the ionizing background, which everyone has to take into account when they make other observations or models or interpretations of observations of metals outside of galaxies, it's inhomogeneous. So just to drive this point home, the mean free path for photons that are at the Lyman limit at redshift of 6 is about 5 co-moving megaparsecs. That was measured recently by George Becker. At 4 Rydbergs, which is the typical energy that you need to ionize from carbon-3 to carbon-4, it's actually quite a bit shorter. No one has measured this because it's impossible at those redshifts. But if you just assume that all the helium in the universe is helium-2, then you get that it's about 270 co-moving kiloparsecs. So it's very, very short. So the flux that you need to generate high ionization ions has an incredibly short mean free path during the reionization epoch. Just for context, the typical distance between quasars is about 100 co-moving megaparsecs. So that means that the average circumgalactic medium at the EOR has never heard of a quasar, has no idea about quasars. The flux that regulates their ionization state is entirely galaxy regulated. This is kind of an echo of something that Joop Shea pointed out in 2006 with regards to DLAs at cosmic noon, but it's appropriate to basically the entire CGM as you go to higher and higher redshifts because quasars are just so incredibly rare. So that's a big difference. A redshift of 2, if you're looking at carbon-4 absorber, its ionization state probably comes from quasars. A redshift of 6, If you're looking at carbon-4, its ionization state has nothing to do with quasars. They're too far away, and the ionizing background is just the opacity is too high. So it's a very different environment. Just a way of emphasizing this within our simulations. So we run reionization simulations, just to quantify how different the ionizing background is prior to the completion of reionization. And just as a reminder, that need not be a redshift of 6. It might have been as late as redshift of 5.5 or so, according to recent work by people like Laura Keating and Sarah Bosman. So what I've plotted here is the predicted ionizing background in units of specific intensity here versus energy here in electron volts. At redshift of 7 in one of our models, it has a plausible reionization history. And in this particular simulation, the neutral fraction is 37% at this redshift here. So this is what the ionizing background looks in regions that are neutral. So the neutral fraction is more than 99%. And you can see you get some nice spectral filtering here because of the fact that this is mostly H1 during your absorption here. And then this is the helium-2 break here. And if you look at ionized regions, the ionizing background is actually quite a bit more intense and has a very different shape. So this is fairly intuitive. In places that are optically thick, you ought to see a different ionizing background than in places that are optically thin. The important thing here is that that could still be the case, even at redshift of 6, even at redshift of 5.5, if reionization completes as late as some people think it does. So that's fairly intuitive. Prior to overlap, the UVB depends strongly on the local opacity. But it turns out that there are small scale fluctuations in the UVB, even at later times, as Yopche was pointing out in 2006. And just to emphasize this point, in 2016, I looked at one of my reionization simulations and looked at where the carbon-4 absorbers were and where the silicon-4 absorbers were in carbon-2. And I looked at what the typical amplitude of the UVB is at the location of these absorbing ions and compared it to the mean UVB, which was predicted by the simulation, accounting for UVB fluctuations and so forth. And I found that carbon-2 absorbers typically see a UVB that's a little bit suppressed compared to the volume average, whereas carbon-4 and silicon-4 absorbers tend to see a UVB that's a factor of 2, 3, 4 times what the mean average is. So this means when you're interpreting low ionization or high ionization absorbers, they don't really see the same UVB. So if you interpret them all using the same UVB, you're off by a factor of 2 or 3, almost certainly. And these simulations, you can make arguments why they actually underestimate these effects here. So UVB fluctuations are things that people need to take into account, and they're starting to be able to do that, which I think is exciting. So having put that physical context in front of us, I want to talk about just qualitative predictions for how the circumgalactic medium gets ionized and enriched. And the important thing that I'm going to keep emphasizing here is that those things happen simultaneously, and you can't pretend that you can interpret your observations in terms of just one effect rather than the other. So here are images of a massive halo that formed in one of our simulations. This is work done by Caitlin Doty. A massive halo that forms, these are just snapshots of the same halo at redshift 8, 7, 6, and 5. And the bottom panel is just the oxygen column density. And what you can see is that at early times, the oxygen fills up some of the space around that halo here, centered on this cross. And as time goes on, it starts to fill in more and more of that region here. So that's kind of intuitive. You form more stars, you form more metals, the circumgalactic medium gets enriched, so whoop-de-doo. However, as reionization proceeds, it also ionizes that oxygen. So if you look at the column density of neutral oxygen here, you find that that doesn't really change too much between redshift of 8 and redshift of 5. So you're making more oxygen, but you're also ionizing it. And if you squint, you might be able to persuade yourself there's actually even less oxygen at redshift of 5 than what there is, our neutral oxygen at redshift 5 than what there is at redshift of 7, even though there's more oxygen overall. So there's simultaneous ionization and enrichment going on during this epoch of reionization, which is not so much the case after redshift of 4, when the UVB is relatively flat in time. And so that's something that we have to take into account. This is another statement of the same phenomenon here. This figure is a little bit busy, so let me just step you through it. Black curve here gives the volume weighted, cosmically volume weighted carbon metallicity divided by what its value is at redshift of 5. So redshift of 5, it's 1. And what this shows you is that at redshift of 10, in this particular model, the carbon metallicity of the universe as a whole is about 1% of what it was at redshift of, or what it got to be at redshift of 5. Okay, so the universe gets more enriched with time. That's fairly intuitive. Again, more stars, more metals, so on and so forth. However, if you then look at the fraction of that carbon that's visible as carbon 2 or as carbon 4, you get more dramatic evolution. This is, you ignore the thin line here. This thick blue line here is the fraction of all the carbon that's carbon 2. And you can see that that decreases because reionization is happening. It goes from some large number down to some very, very small number by redshift of 5, whereas the fraction of the carbon that's carbon 4 actually increases, right? So if you want to look at evolution in carbon 4 or evolution in carbon 2 and interpret that purely in terms of metallicity evolution or purely in terms of reionization, you can't. You have to take both of these effects into account here, because ionization and enrichment occurs simultaneously at this redshift. And so this kind of figure here makes the fairly intuitive prediction that you should see more low ionization ions at high redshift and fewer high ionization ions. So this was, something that we put forward in 2015, at least qualitatively. And people have definitely seen that now. This is a nice paper by Thomas Cooper, where they look at absorption systems at redshift of 5 to 7. They look at a whole bunch of systems selected in such a way that they have coverage both in carbon 2 and carbon 4. And for some interesting reason here, which we don't totally understand, below about redshift of 5 3/4 here, most of the systems are visible in both carbon 2 and in carbon 4, whereas above about redshift of 5 3/4, you generally only have limits on carbon 4, but you do detect carbon 2. So it seems that most of the carbon is tending towards being carbon 2 at high redshifts, and quite a bit of it is turning into carbon 4 at low redshift. This is qualitatively in agreement with what comes out of the models here. Now, actually doing a quantitative assessment of whether this is whether this figure gets predicted by the models, we haven't done that yet. Would like to do that at some point, but anyway, there's qualitative agreement that there's this evolution going on. So you do have more low ionization ions observed. This is another demonstration of that, again, in this paper by Caitlin Doty. What she did was she looked at the line incidence of neutral oxygen absorbers. This thing on the y-axis here, that's called line incidence, or DNDX for observers, for absorption-based observers. What that means is the number of absorbers per quasar, if you like, or per unit distance along quasar sight line. And what she finds is when you look at the models, between about redshift 8 and redshift of 6, the line incidence of oxygen 1 absorbers is relatively constant, which is basically a competition between enrichment and ionization. Enrichment makes oxygen go up, ionization makes the oxygen 1 fraction go down. They sort of cancel. So the amount of oxygen 1 is relatively flat. And then all of a sudden it drops to the floor at about redshift of 6, which is the time when the neutral fraction of the universe goes to 0 because of reionization, and the time when the ionizing background jumps up. So all of a sudden, a lot of the oxygen switches from being oxygen 1 to oxygen 2, and the abundance of oxygen 1 drops. This is much more visible for weak absorbers than for strong absorbers, but it can still be seen. And this was put out in a prediction paper in early 2019. A few months later, the observations came out by George Becker that showed that this really does seem to be happening in the observations. So it's a complementary test of when reionization actually happened. And once again, a statement that enrichment and ionization happen together, and you have to take them into account. All right, so that's a little bit of an overview of the physical evolution of the state of the CGM. What I want to talk about now is this nascent field of relating absorbers to the galaxies that are in their environments. This has really exploded over the last 10 years, and it's going to get even bigger with JWST. I can't even scratch the surface of this, but I can talk about it just to stir the pot and get us all thinking about it, because I think the relationship between absorbers and their galaxies is going to be increasingly important as time goes on. So let's think about this from an intuitive perspective. I'm going to focus on carbon 4, but you could say things like some analogous things about other ions. The amount of carbon 4 that's around a galaxy depends on the amount of carbon that you make per unit of stellar mass formed, the carbon yield, and that has contributions from AGB stars and type 2s and so forth. It also depends on the fraction of ionizing flux that gets out of galaxies, because if more high energy flux gets out, then more of your carbon will be carbon 4. It depends on your feedback prescription. And this bit's a little bit counterintuitive. Alireza Rahmati showed in 2016 that if you have weaker feedback, then you tend to have more metals in your CGM because you generate way more stars, and the fact that you've generated way more metals overcompensates for the fact that a smaller fraction of them wind up in the CGM. So if you have weaker feedback, you have more metals in the CGM. So that's another sensitivity here. And as I mentioned, other ions have analogous sensitivities to these factors here. So let's pause for a second and think about what that means. Suppose that galaxies are very efficient at making some ion. In that case, if you see an absorber in that ion, you should expect to find relatively few galaxies around it because it only takes a few galaxies to make that kind of cloud. On the other hand, if galaxies are highly inefficient at making a particular ion, either because they don't make very much ionizing flux or because they don't make many metals, then you need to have a lot of galaxies to produce a cloud of a given strength. So that means that by counting the number of galaxies that you find around absorbers, irrespective of what the physical properties of those galaxies are, that's also interesting. But just by counting neighboring galaxies around absorbers, you can learn something about yield and about the ionizing escape. And this is more effective at the EOR than it is at low redshift because the ionizing flux in the metals are still produced quite locally. So here's a more specific case of what you can learn about ionizing flux. This is something that I like to think about here. So one question that all modelers confront is how does ionizing flux get from stellar photospheres into the CGM and into the IGM? And it's a difficult problem because it involves very small scale physics. So there are two extreme models for how this might happen. In one case, this is called the ionization bounded nebula or the picket fence model. The ISM consists of opaque regions and optically thin regions. And so the flux that gets out from star forming regions is equivalent to stellar photospheres multiplied by some factor of 10% or 20% or what have you. But the flux that gets out has the same shape as the intrinsic stellar photospheres. That's one, in my opinion, relatively extreme model. It's the most popular model by far. But there's another model, which I think is equally extreme, but no more extreme. That's called the density bounded nebula. In this case, the entire ISM consists of a translucent membrane, sort of like wax paper, which tends to let high energy flux out, but not low energy flux because of the fact that cross section goes down as the energy goes up for photoelectric transitions. And so in this scenario here, high energy flux tends to get out of galaxies more easily than low energy flux. So this is the ionization bounded case, which is assumed in just about all 1D models of the UVB, the Hart-Medon and the Fauché-Giguère and the Curie and Srianand. They all assume this scenario here. This is the alternate an equally extreme model. The real universe is probably somewhere in between, where you've got some optically thin and some optically thin regions. But I just want to point out that whereas this is the one that's always considered in the literature, this one I think is equally plausible and has interesting implications. So as an example of how ionizing escape introduces an additional dimension of uncertainty when interpreting observations, what I've plotted here is something called the column density distribution. So that's the number of carbon-4 absorbers per strength at a redshift of 6 in the models here. So this peach colored region here, or salmon, whatever color that is, gives you the column density distribution predicted out of the box by the simulations. That's in the ionization bounded case. If I then go back in post-processing and change how ionizing flux gets out to match the predictions from the density bounded scenario, then suddenly I have quite a bit more carbon-4 here. And these are Valentina's observations here. And what you can see is that in the default model, there's not nearly enough carbon-4. And if I just change how ionizing flux gets out without changing the number of stars or the number of metals, or even changing the amplitude of the UVB at the Lyman limit, then I can get quite a bit more carbon-4. And the impact on silicon-4 is actually quite a bit weaker because silicon-4 is a somewhat lower energy transition. So I can get more silicon-4 and more carbon-4 for the same star formation feedback and H1 Lyman alpha forest within one of these reionization simulations. Really, this is the only observable here that tells you, in this case, about how ionizing flux gets out. So what that means is that the energy dependence of ionizing escape is really just as important for understanding CGM observables as star formation and feedback. And the CGM environments actually probe this dependence. So this is one sense, and the CGM observables by themselves probe this dependence. That's shown in these figures here. But the environment actually shows this dependence as well. This goes back to this whole counting galaxies idea. Again, if galaxies are more efficient at producing the relevant ionizing flux, then you need fewer of them to produce a carbon-4 absorber. And that's shown explicitly here. Here on the x-axis is the UV luminosity and of simulated galaxies here. Here's the expected number of neighboring galaxies around strong carbon-4 absorbers as a function of their UV luminosity. And of course, you have lots of faint things and very few bright things. So if we just compare the green and the red curves here, you immediately see that in the density bounded case corresponds to the situation where galaxies are efficient at releasing high energy flux. You need fewer galaxies to produce a given carbon-4 absorber. Whereas in the traditional ionization bounded case, you need more galaxies. So in other words, if galaxies are brighter at higher energies, then you need fewer of them to find a carbon-4 absorber or to make a carbon-4 absorber. And really doing this should be child's play with JWST. There should be plenty of galaxies around most strong absorbers. So I think this field is going to get even bigger as time goes on. So that was something that we put forward a couple of years ago. I have a student working with me right now who's asking a similar question. Again, I mentioned that the abundance of absorbers depends on the yield and the ionizing escape. So she's looking at the yield. So she'd asked the same question: how many neighboring galaxies do you expect around a strong absorber as a function of their UV luminosity? In the case where you just assume that the simulation got it right in terms of the carbon yield. That's the blue curve here. So you have a certain number of faint galaxies expected around an absorber and a smaller number of bright galaxies. But then if you multiply all the metallicities by 4, which is equivalent to saying that we underestimated the carbon yield in the simulation by a factor of 4, then you don't need nearly as many galaxies to produce an absorber here. So there's additional information, thank you, about the yields as well. All right, so you have degenerate constraints on the yield and on the ionizing escape. And one question I'd like to ask is, if you look at the environments of low and high ionization ions, can you break this degeneracy? All right, so there are some observational challenges that I'd like to talk about. First of all, if we look at the equivalent width distribution of carbon-4 absorbers at slightly lower redshifts here, we find that the models overproduce faint absorbers and possibly underproduce strong ones. This is a fairly generic issue with models. This is a paper by Simeon Bird. I forgot to put his name here. But anyway, you can see the same result, that the shape of the carbon-4 equivalent width distribution in the default illustrious model is just incorrect. So you can fiddle the outflows and the ionizing background to improve agreement there, but it's kind of unsatisfactory how it is right now. And of course, this problem actually gets worse as you go to higher redshift. This is the equivalent width distribution. This is the line incidence of weak absorbers and strong absorbers. So we don't really understand the current observations. Here's another interesting result that Yunjing Wu put out a few years ago. He got ALMA time to look for carbon-2 emission for galaxies associated with a strong O1 absorber. And he mentioned this to me, and I looked in the simulations and I said, don't bother, you're never going to see anything because the host galaxies of O1 absorbers tend to be incredibly faint. ALMA's not going to see anything fainter than about this. So I was just about to send him an email telling him, don't even look at your data, it's not worth it. When he looked at his data and found a 4 sigma detection of carbon-2 emission around his O1 absorber. So that was a big surprise. So there it is, got a Nature paper out of it. So this is the typical luminosities of associated galaxies that are expected to be associated with O1 absorbers in the model. This is the one that he found. It's way, way, way brighter. Something like a factor of 10 to 100 brighter than anything that we would have expected based on the models. So this tells us probably that the models depend too heavily on low mass galaxies to account for all the metals that are in the CGM, and that we need to think more carefully about what's happening with the massive galaxies. This is something that Mark talked about yesterday. He noted that in his observations, he finds that the metallicity of DLAs seems to drop to the floor around redshift of 5. This is not expected in 2 different hydro simulations that Sultan Hassan looked at back in 2020. So if Mark continues to find these low metallicities, that's going to be a problem for us. Let me just, let's see here. Let me take 30 seconds and go through the challenges that we are going forwards. I know I'm out of time. Low resolution, we need to account for dynamic range issues, obviously. It's been shown this is especially an issue for low ionization absorbers. Douglas mentioned that we have to account for mixing going forwards. There are a number of groups now accounting for rad hydro, which is great. This is a paper by Harley Katz from a couple of years ago where they're accounting for UVB fluctuations. That's nice because it accounts for UVB and homogeneity, but it does introduce new parameters, the choice of the emissivity model and how ionizing flux gets out of galaxies is something that we have to worry about. And of course, energy resolution. Typically these models have, half a dozen energy bends compared to the hundreds that may be necessary for certain things. So going forwards, it's always important to anchor our models in existing observations. I don't think we actually can understand from a theoretical perspective the equivalent width of carbon-4 absorbers, silicon-4 absorbers yet. There's always more work to do to leverage, observations of different phases at the same time. I think there's a lot to be learned from matched observations of absorbers in galaxies. Obviously, we could always improve our numerics, but let's make sure that we're doing stuff that's observationally relevant. And I think the most important point of all is that no one's going to get all the details right. No one's going to account for all the physics. It's always going to be necessary that we have a dialogue between, for example, the Zoom simulators and the cosmological simulators. Okay, that's it. Thanks.
Thank you, Christian. Thank you. So we have time for a couple of questions. If there are any, just raise your, okay, there is one from on the Slack by Isliang Yu. Thanks, Christian. You mentioned that the impact of QSO on CGM is small at high Z, but I saw some studies suggesting that the extended high Z Lyman alpha halo cannot be explained without QSO feedback, expelling the gas out of the large scale. Is the result from this kind of simulation sensitive to the QSO feedback prescription? It's a long question.
Right. So we're talking about slightly different things here. What I'm talking about is the radiation field. Certainly, if you were talking about Lyman alpha halos, those tend to be like Lyman alpha blobs. They tend to be regions around, forming groups, for example, where you've got very extended gas that's probably been thrown out by a huge amount of star formation activity and possibly feedback from the QSO, and then it's been irradiated by the QSO. Those are special regions. The universe as a whole is optically thick to flux that's more than a couple of Rydbergs in energy. And so the average CGM does not see light from such regions, even though those regions themselves obviously do depend on the feedback from the quasar. Hopefully I answered the question.
So I don't see other questions. I can ask one. So when you compare the ionization bound and the density bound scenarios with the absorbers distribution, so it seems that the density bound is a better, provide a better fit description. However, in the ionization bound scenario, I mean, these are somewhat degenerate in the sense that you can have the ionization bound scenario with sort of larger holes, and therefore you can have also larger fraction of high energy photons escaping. So I think what would be more instructive is comparing with, again, with the ratio between carbon-4 and carbon-2 to distinguish between the two scenarios to avoid this kind of degeneracy. So have you investigated that?
Yes, we did look at that in this paper. I completely agree with you. I think looking at one ion is never the whole story. So what we found is that the density bounded scenario does enable us to do a better job with carbon-4. It causes us to do a worse job with carbon-2. So the carbon-2 is already underproduced. If we then release more ionizing flux, it gets even more underproduced. You can make some progress by adjusting the carbon yields, but it doesn't completely solve the problem by itself. So in that case, my first guess would be just that we have resolution limitations, and carbon-2 absorbers are really small things that are not possible to resolve in cosmological simulations. That's a bit of a cop-out though. And I think the most honest answer is that we don't have the full story.
Okay, thanks. Very interesting. So if there are no more questions, I can't see any, but the organizer, please prompt me if I'm actually not seeing them. Thanks, Christian, again. And we pass to the next speaker, Tom Spax. Tom, can you share your presentation?
Yeah.
Perfect.
You can all hear me clearly?
Yes, yes, clear, crystal clear, at least on this end.
Okay.
So you can start. Thank you.
Yeah, thank you very much for organizing this conference as well. And it's a combination of a discussion about dust and a discussion about metallicity. So I'm trying to bridge a little bit more towards metallicity in this discussion. But in essence, it is a discussion about dust-obscured star formation in the early universe and trying to get a clear picture of this using direct observations. So the initial discovery of dust in very high redshift epoch of reionization space in 2015 by Watson was quite surprising, because in order to form dust, metals have to be developed that produce the dust, and initial UV observations didn't suggest much to the same effect as severe dust obscuration. So this discovery was interesting and resulted in a lot of follow-up. And in 2019, roundabout, there originated the dust budget crisis, where the amount of dust-obscured star formation that was seen from all these mostly single data point observations with ALMA were unable to be explained by a stellar population that was seen in the UV. So using typical IMF constraints, you can predict how many supernovas there must exist, or how many AGB stars must contribute towards the dust production that is seen with ALMA. And these typically are not able to explain the dust that we see at higher redshift. Or we need to assume that there is no dust destruction, typically through a reverse shock, when compared to local supernova dust production mechanisms. Another method to form dust that, again, depends on metal production, typically through supernovas, is grain growth in the ISM. So at about 10 to the power 8.5 or so stellar masses and a metallicity of 0.2 or higher, the ISM is able to become an environment in which dust can grow and can become a dominant factor towards the dust production at high redshift. So by understanding dust, we can also directly link that to the metal production at high redshift. And this is important if we want to understand basic questions such as what fraction of stars formed in the early universe remain hidden behind clouds of dust, and which ones are covered in deep UV pencil beam observations that are able to probe all the way to redshift 10. This is a study from 2018. However, in the recent years, some impressive studies have been pursued and shifting essentially the infrared incomplete part a little bit to maybe one redshift higher, but there exists a large variety in the different results that we get from different surveys. Another important contributor or method of study that we have of the dust is by comparing the UV slope, so where the light is absorbed by the dust, according to a dust attenuation curve, which is dependent on dust properties, dust composition, all these things that are all very intrinsically linked to the chemical evolution of the early universe, and compare that to the infrared emission that we see at the long wavelength range. Finally, a thing to note is that by using metallicity estimates from optical or also submillimeter spectral lines and dust mass, we are able to predict that there must be older pre-existing stellar populations at redshifts of 15. So this is work by Yuichi Tamura, but also Robert Berstani in 2020 did an excellent study on this. And we can thus probe well within the first galaxies before even having to rely on the James Webb. One big if that is hovering over all of this is the dust temperature, the dust temperature. So the dust mass, the dust obscured star formation rate, the IRX, the luminosity, all these form an integral part towards studies of dust properties and thus also of metallicity evolution through dust. However, the evolution is very, very dependent on the dust temperature. With a beta of typically around 1.5 or 2, this means a temperature dependency of temperature to the power 6. And this becomes, as people understand, predominantly more influential towards higher dust temperatures. And these higher dust temperatures have recently been indicated towards with stacking experiments and previous observations. So this is an example of the recent Cosmos catalog, where stacking allowed people to find an increasing trend in the dust temperature. There are many issues associated with stacking, so at least we need to confirm this with individual observations before we actually shout eureka. But it is indeed very important that we understand the dust temperature, particularly to the high redshift range. So initial observations at redshift of 8, in this example, in the paper that we published in 2020, we found oxygen 3 and neighboring dust continuum, and we found C2, but no neighboring dust continuum. So like a seesaw, we were able to pin one of the continuum points very nicely, but managed to drop the other point down significantly, indicating that there exists a large amount of emission that is in the short wavelength ranges associated with very hot dust temperatures. We are able, for a beta of 2, to put the dust temperature at around 80 Kelvin, and that would put this galaxy in the Euler range at a redshift of 8.3. Clearly, we need short wavelength observations, and that's exactly what we did in 2021. So while ALMA was not operational, we were able to use archival data to study the short wavelength dust properties of the famous Watson 2015 source. So using the band 9 data that you can see here in the dust SED, we're much better able to constrain and follow the shape of the spectrum compared to the dashed lines, which is prior to the band 9 data. Indeed, we provide now a complete coverage of the submillimeter emission, and that's reflected in the following table. We also compared to a different method, but I hope Laura will later talk about that. So I refer to her talk there. But here I want to just briefly compare a couple of numbers. And while it is very, it's aesthetically maybe not pleasing to look at a table, but the numbers all appear relatively similar. However, the thing that is vastly different is the accuracy. And here it is very important to note how important the accuracy is, because of the very strong dependence on dust temperature, a little bit of scatter goes a long way. We find that the dust mass relative to the supernova is in line with dust production models of this galaxy, and also that the majority of the star formation rate in this system is dust obscured. Here again, I want to use a graph to notify or explain why it is so important to constrain the dust temperature. So summarized in a nutshell, one 60 Kelvin galaxy can outshine 10 40 Kelvin galaxies. So there exists a sort of Eddington bias towards the higher redshift range of these galaxies and their contribution to the cosmic star formation rate, where a small scatter upwards is vastly compensating for a small scatter downwards, and thus understanding especially these warmest galaxies in the early universe is very important towards a complete picture of star formation out to well beyond the epoch of reionization, and preferably also when James Webb starts observing galaxies. Clearly, the next step is observing more of these high redshift galaxies with short wavelength observations. And adequate constraint can only come when we probe at the peak of the spectrum. For our ZD1 galaxy, we managed to do exactly that with the band 9 observations. However, there exist a couple more galaxies in the epoch of reionization that can do with these band 9 or band 10 observations. Just quickly want to note that the sensitivity of band 10 is lower in such a way that band 9 is almost always preferable in constraining the dust temperature. However, moving forward and constraining the dust temperature will be very important to use the short wavelength capabilities of ALMA. These are relatively expensive, time-expensive observations, but without a direct constraint, we can basically not say a lot about them. So again, even this normal galaxy at a redshift of 7 with a UV visible star formation rate between 4 and 6 has 85% of its emission. Okay. Well, perfect. I'm already concluding, so we have time for questions. Okay. Even this normal galaxy is 85% dust obscured. And we can only determine the dust temperature of these high redshift galaxies through direct observations. Particularly important is that the larger scatter, particularly at the higher temperatures, could lead to a systematic offset in our understanding of the high redshift evolutionary track of galaxies, and more short wavelength observations are necessary to answer the role of dust in the high redshift universe. Thank you.
Great, good, excellent, very nice and perfect timing. Thanks for staying in time. Right, any questions? I don't see questions on Slack, neither hands raised, so this gives me the opportunity to ask questions myself. So the constraints on the temperature is impressive. However, you do make some assumption on the emissivity, which at these early epochs may change significantly because the dust properties may evolve drastically. So I don't know how you fit for the emissivity as well.
Yes, we are able to. So actually, this is not a complete story where the dashed lines, we have to fit the emissivity to between 1 and 2 or something. But we can freely let the beta roam free in this example. So actually, even in the long wavelength sense, because we now know where the peak is, we can measure the tail. So yeah, even the beta you can constrain with these observations, and that's again important for understanding the chemical evolution of dust at high Z.
Great. Christian has a question.
Thanks. Very nice work, very detailed work. I appreciate how much you emphasize that the luminosity is sensitive to the dust temperature. That seems to be a very important point that keeps coming up. Your final slide there notes an 85% dust obscuration fraction. Can you draw a connection between that and escape of optical or even ionizing flux on the one hand, or the concept of a dust covering fraction of the ISM, or what does that 85% number mean?
I'm not entirely familiar with the effect on ionized emission that escapes from the galaxy. Unfortunately, I'd have to refer you to other people for this. But indeed, it just means the fact that these galaxies are selected to be UV bright to begin with, and then we go look and still find them to be, vastly dust obscured. That does mean that a large portion of the part that is dust obscured, I don't expect a lot of ionizing emission to escape from these regions. So their contribution must be limited in a certain way, but I'm not an expert on reionization processes.
Okay, yeah, I'm asking because if you get simultaneous constraints on 3 or more hydrogen recombination lines, like H alpha, H beta, H gamma, or bracket gamma, or Paschen alpha, or whatever, any 3 of those, you get an independent constraint on the dust covering fraction. And it would be interesting to ask the question whether JWST would permit us to get a complementary measurement of that 85% number and see how it compares with what you're getting. Okay,
can I just pick your brain for 1 second?
I can send you a reference. Yeah,
that'd be very, very interesting, because I'm also considering, and not every part of the galaxy is equally warm as well. So perhaps that a couple of bright spots are dominating the SED of this galaxy, and with a dust covering fraction, you'd be able to better trace the patchiness as well.
Absolutely, yeah.
Okay, thank you.
Okay, there are a couple of questions on Slack, but I think we are running a little bit behind schedule. So maybe you can answer those directly on Slack. So we move to the next
Thank you.
speaker. Thank you, Tom. It was a really nice presentation. And next we have Joris Wittstock, and on the dual constraints with ALMA, and you see the whole title there. Joris, maybe you want to switch on your camera so people can.
Yeah, I should.
You want, otherwise.
Can you hear me?
Yep.
Yeah, great. Okay. Yeah, thank you, and thank you to the organizers for putting up this really nice meeting. My name is Joris Wittstock. I'm a PhD student at the Kavli Institute, and yeah, this is a very long title, but I think the main part about this are the first two words, really, because in this meeting we're talking about metals and dust, and these new ALMA observations that I'll be talking about, they give us exactly, they can teach us about those two things, so we can look at the metal cooling lines in the far infrared and get simultaneously dust continuum measurements. So just to very briefly set the scene, I think we're going to hear, we've already heard from Tom about ALMA, and we'll hear much more in this session, but why ALMA is so powerful, especially to look at systems in the epoch of reionization, is that if you want to do any spectroscopy, the rest frame optical, until we get James Webb, you're restricted to low redshifts. And then even if you go to the rest frame UV, well, there's very weak lines. Lyman alpha you can observe, but only up to a redshift of 7. While ALMA already gives us, through most notably the C2 and O3 lines, a very powerful tools to study galaxies in the early universe. And so in this talk, I'll present new measurements of 5 galaxies. And so these were galaxies that were initially spectroscopically confirmed with C2 by ALMA. And then we followed up with oxygen 3 88 micron measurements. And just to quickly give an idea of what kind of galaxies these are, they're UV bright. They're normal star-forming galaxies at this redshift, so they've got star formation rates of between about 20 and 80, stellar masses in the range of a few times 10 to the 9, and they've been selected using their oxygen 3 and H beta equivalent width, which just helps using the Spitzer photometry to really narrow down the photometric redshifts, which then allowed ALMA to perform a very efficient spectral scan. So taking a look at this new data, the oxygen 3 measurements I'm showing here in red contours on top of the rest frame UV. So this very highly ionized line, we expect to trace the UV bright star forming regions, which indeed we do see generally. But there are some imperfections to the overlap. So for example, in the middle here, you can see, although we see 2 components in the rest frame UV, interestingly, the oxygen 3 only seems to be coming from this patch on the right. And as I mentioned, we don't only observe the oxygen 3 line, but we also get dust continuum measurements where we don't actually detect any of the 90 micron dust continuum, except in this one source, where we get this very compact emission at 90 microns. And I'll talk about this at the end of the presentation. But first of all, just zooming in on the emission lines. So in this plot, in the top panel, I'm showing you the oxygen 3 over C2 line ratio, which is kind of the natural thing you can look at. And this is in the top panel plotted as a function of the equivalent width of the optical lines again, which is, you can think of as an inverse age tracer. And you see this very nice correlation, both in the gray points, which are local metal poor dwarf galaxies, but also in the galaxies at high redshift in our sample. And if you overplot some simple cloudy ionization, photoionization models, indeed we need young stellar populations and a high ionization parameter to reproduce these values, which on its own is not very surprising. But then going to the bottom panel, we're zooming in really on the oxygen 3 luminosity here, where you can already see the data points at high redshift seem to lie just a little bit above the typical values at low redshift. And indeed, if we try to reproduce these values with our models, you can see this orange line in particular. This is a model with a near solar metallicity. And so it seems we can only reproduce these values with an almost solar metallicity, which initially might seem a little strange at these very early epochs to already have such a high metallicity. But it is in line with some of the recent findings, actually, and also some of the work that's already been presented in this meeting. So one other thing we looked at was how this line ratio varies both between our sources, but also on a spatially resolved scale. So we see a range of values globally across the galaxies, ranging from about 2 to 10. And then also you can see these maps here show the line ratio spatially resolved. So going from the black-gray ratios of about 2 to 3, all the way to the dark red where it's 10 or even above. And in this source in particular, we see this gradient in the line ratio, where interestingly, you can see that the gray dust continuum contours seem to align mostly with the side of the galaxy with the lower line ratio. And well, that's just one example in this galaxy, but we have looked at this a little bit more quantitatively across bigger samples. So again, the gray points here are local galaxies, both metal poor dwarf galaxies and ULERGs. And you can see there's this tentative anti-correlation if you plot the line ratio as a function of dust obscuration, which here we've measured in the IRX axis, so infrared over UV luminosity. And you can see both in these local galaxies, as well as tentatively in our sample, the open circles, you can see this anti-correlation. And we, the points we try to sample on a local, so spatially resolved basis, the squares, you can also tentatively see this trend. And so that's quite interesting that these high line ratios only seem to occur at low degrees of dust obscuration. So then in the final part of this talk, as I mentioned, I'll talk a little bit about the dust properties and why is it interesting to look at dust, specifically at high redshift. I think we can really learn a lot about this, what Tom also referred to, since for dust to form, we first of all need to build up the metal content of a galaxy. And so because these galaxies are so young, they really haven't had much time to build up their metals and convert it into dust. So we can really start to constrain the yield of metals and dust in these systems. And we can, for example, compare it to the theoretical yield for example, supernovae. And second of all, we also expect to see higher dust temperatures just because at high redshift, higher specific star formation rates means we get more young, massive stars that just heat up their surrounding dust. And if we have a look at observations and also models, this is indeed what we see. So as a function of redshift, I'm showing the peak temperature of the SCD here. So we see this general rise towards higher redshifts. All right, perfect. And yeah, I think at the highest redshifts, what we can see at the moment is that there's just this large scatter between galaxies. And I won't talk about this too much because I think there's also going to be more on this later, but I think what is good to keep in mind here, and what we found in this case, the one source where we do have two detections at two different wavelengths, we see this very extended emission at 160 microns at the long wavelengths, whereas we only get this compact component at 90 microns. And so the temperature plotted here is only for the compact component of the galaxy, where you see a relatively high hot dust. But so this extended emission would suggest that actually there might be a much more extended dust reservoir, which is probably a lot colder than the compact component. And we also found this one source having a very low dust temperature, coming only from a detection at 160 microns and an upper limit at 90 microns. And this is also very interesting on its own because it implies a very high dust mass, having a low dust temperature, which then means you need to create a lot of metals in the first place and convert them into dust very efficiently. And so this might imply, for example, the need of a top-heavy IMF and other dust production mechanisms than supernovae on their own. So I'll very quickly mention that one thing we've been looking at is a larger sample of high-redshift galaxies and trying to constrain this beta parameter, so that basically the slope of the Rayleigh Jeans tail, which was also mentioned in the previous talk. And we don't really see any strong evolution, it seems, but there are some interesting trends with other properties. And so it seems at high redshift, the galaxies line up more with local ULERGs than with star-forming galaxies. A range of oxygen 3 over C2 ratios, both on a global scale and also locally, which might be anti-correlated with the dust obscuration. And then we've seen a trend as well with the equivalent width of the optical lines and needing this very near solar metallicity to explain the very high oxygen 3 luminosities. And finally, I've shown you measurements of the dust, where there's one system in particular seems to have a very high dust mass and therefore potentially needs a very high metal and dust yield to explain what we're seeing here. So I'll stop here and take any questions.
Thank you, Joyce. Very, very nice. I don't see questions yet on Slack or yes, there is one. Christian is asking, your talk made reference to AGB stars. Is there evidence that they contribute new metals prior to Redshift 6? This seems like a very important question for understanding early carbon abundances.
Okay, yeah. So in this case, I would say it seems like AGB stars can't be very important just because of the timescales that are at play. So at this redshift of about 7, you just don't have enough time basically to really have AGB stars kick in and produce enough dust to explain the quantities that we're seeing. So from that perspective, I would say then they don't seem to be, or at least, in most works, it seems that AGB stars have been ruled out as a major source of dust production. Hope that answers the question.
Hopefully. So there is one question by Laura on the chat. So hi, Joris, nice talk. Can I ask the dust to stellar mass ratio in the coldest and more dust massive source you find?
Yeah, that's a very good question. So, well, I should say we only, of course, have this one detection combined with an upper limit. So really what you ideally want to do is get more measurements to really accurately constrain the dust mass and the dust to stellar mass ratio. But for the moment, it seems with this really high dust mass, it could be anywhere up to a couple of percent of dust compared to the stellar mass.
Right. Good. So there is another question by Yuji on Slack, but I think you can respond to that on Slack because again we are running on schedule. Okay, thanks again, Joris. And then we have Joe Lewis. Joe, can you share? Okay.
All good.
Fantastic, perfect. So please, Dustin, the epoch of reionization, and the rest of the title is there. Thank you.
Hi, everyone. So I'm Joe Lewis. I'm a postdoc in Heidelberg currently. And I want to talk to you today about a simulation that's very originally called Dustier for an even more original dust in the epoch of reionization. Yeah, I know. And the idea is to look at a much more cosmological context for dust than the previous talks maybe. So the motivation here has already been covered fairly well by all the other talks. And I guess the main points are, we know now that there are significant dust masses in the massive galaxies in the early universe, including during reionization. And so this implies several things that have also been covered and that interest people who study reionization like me. These are, well, if these galaxies are very dusty, then it's possible that, and it's actually been shown, that a large portion of their UV and then potentially ionizing light can be obscured by this dust. So this does two things. It means that we might be underestimating the number of massive bright galaxies, which is important in trying to understand which galaxy is driving this reionization process. So I guess that's from an observational point of view. And from a purely simulation point of view, for the same reasons, we might be overestimating the impact that these massive galaxies are having on the local IGM that surrounds them. So they might actually be ionizing, have less effective ionizing luminosity that's reaching the IGM. And so this is just a quick plot showing you a compilation of compilations of dust constraints that we have from the literature as a function of stellar mass. Yeah, and so the idea is to couple a model for dust into the already, I would say, successful RHD simulation code that I've been using, and that was developed in Strasbourg with my PhD supervisor. And so with the help of Johan Dubois, we coupled his dust model for production and destruction to this code. And so I don't really have time to go into the nitty-gritty details, but I think some of the main assumptions are the following: that we treat dust as a passive scalar in our simulations that represents a full population of grain sizes, of which the average size is 0.1 micrometers. And we also assume an average solar composition for the chemical composition of the dust. And so an important point as well is that we couple the dust to the treatment of photons that we perform in the ATON module of the code. So it's coupled to the radius transfer. So dashing forwards, this leads us to the dustier simulations that use this code. And so one of the features is we have a full speed of light for the radiative transfer. This is a moderate box. It's only 16 co-moving megaparsec over H per side. So this has implications for some of the reionization and galaxy statistics we'll go into later. We can get back to that. It shares resolution with our larger runs, the Cosmic Dawn 3 simulation that we ran a few years ago as well, last year. And so an important note as well is that our setup does not include AMR. So we're working with a fixed grid resolution here, which is in stark contrast to a lot of the things you've been seeing. And so we have a very coarse resolution compared to the other theoretical work you've seen here so far, of about 1.6 proper kiloparsec at a redshift of 6. And so all this dust modeling is definitely subgrid, right? So if I can go forwards, I just want to show you at least one statistic about the dust in the galaxies. So I'm reprising the plot from earlier, into which I've added the median dust mass to stellar mass relation for the dustier galaxies. And you can see it's this pretty straight looking power law here that has little redshift evolution, and it fits relatively snugly into the locus of high stellar mass, high dust mass constraints that we have so far. And so these remarks go for the other dust statistics, shall we say, that I compute and analyze, but I don't have time to go into them today. The idea of our calibration is to try and go for them, how can I say it, to aim to reproduce the maximal impact that dust could have on reionization, and that is permitted by the constraints. So all of the dust statistics are rather high, like here. So the next step is to actually work out what these dust masses are doing for our UV and for our ionizing photons. And so to do that, we need another free parameter, and that is, or several actually, which are the dust attenuation coefficients as a function of wavelength. So to determine these, or to choose the ones that we use, we reprise something from the literature, which is to take several sets of these dust attenuation coefficients and compute the UV continuum slopes of our galaxies for each of these sets. And then we retain the set that allows us to best reproduce the median beta UV slope to magnitude relationship for our galaxies. So this is the relationship I'm showing to you on the left. And the median relationship is shown by the full purplish line, and the distribution extent is shown by the shaded area behind. So you can see that with respect to the observations, which are denoted as markers here at Redshift 6, we have a slightly steep relation, but is overall a relatively good match. Okay, the fact that it's steep actually goes hand in hand with this idea of having being at the upper limit of what's permissible by observations. But it is of note that most other theoretical works have a gentler slope. Okay, so another thing we can do is we can look at the evolution of the beta of our galaxies, which is in the right-hand plot, as a function of redshift. So we do this for the magnitude, roughly magnitude minus 19 bin, and we get a very good agreement here with what observations are showing. So this is a sign that the underlying distribution of betas for our galaxies, including reddening from dust, are actually quite realistic. So I'd like to move onwards to some of the, at least a tentative answer to some of the titular questions. And the first one is the effect of dust on the ultraviolet luminosity function or extinction. So here I'm showing you 4 sets of UV luminosity functions, various redshifts. So the top purplish color is again redshift 6. And then the other colors have been shifted here in this plot so as to be able to easily distinguish them. Okay, so they've been scaled down by successive factors of 10. So focusing on the redshift 6 plot, you can see in 4 lines the extincted ultraviolet luminosity function and the ultraviolet luminosity function before we apply any extinction in the dotted lines. So you can see here that, as expected, extinction is driving the UV luminosity function down at the bright end, quite significantly so, and even at relatively higher redshift. So if you look at the green curve, that's redshift 8, and there's already a significant effect here. So bear in mind that this is a small box, and so the number statistics here on this bright end are quite weak, as you can see actually by the place where I have no data to show you. So the final statistic I want to talk to you about is maybe much more reionization oriented, and it's the luminosity, ionizing luminosity weighted ionizing escape fraction for galaxies in the dustier simulation. So you can see this as the fraction of ionizing photons produced actually make it to the IGM. And so these two orange and blue full curves you see in the plot represent two different cases. The blue curve represents the case where we only consider absorption from neutral hydrogen in the resolved cells in our galaxies. And the orange case is where we also consider the effect of dust. And so what you see in both cases is that the trend is globally similar, and dust has a small effect that starts to appear towards the end of reionization between, I don't know, 6.5 and 5. And so overall, this is, I didn't have the time to introduce the plot, but this is being driven by more and more massive galaxies appearing. And so in this weighted average, they are driving down the mean escape, if you will. But the takeaway from this is that the main trend is still driven by the hydrogen gas, of course. And so while this is going to favor slightly reionization being driven by smaller, fainter galaxies in your box, it will not take you all the way from reionization driven by bright galaxies to a faint driven reionization scenario. And so that takes me to my end slide. Thank you for your attention, and please, if you have any questions, I'm sorry I had to go so quickly through a lot of the technical aspects here. Hopefully you were able to follow. Thanks.
I think it was very clear. Thank you very much, Joe. So there is a question by Christian. Does the predicted weighted ionizing escape fraction have any energy dependence?
So no, this is one of the, hearing your talk, this is one of the things I thought you might ask. And so no, for now, this is all in one frequency bin, I'm afraid.
Young Queen is asking, sorry, I missed it, but could you explain again the dependency of attenuation on magnitude in the luminosity function plot? Why faint galaxies show no attenuation at all?
By fate, you mean, so the left-hand side here, you expect?
I guess so.
Okay. This doesn't surprise me that much, but so there is some attenuation. I can say that, so there are many orders of magnitude on this plot.
Yeah.
I don't have a number to tell you that there is some, but it's very small. So we don't have very high dust masses in our small galaxies. I'm trying to think of the conversion here, but we actually find dust mass jumps quite significantly from between something like minus 15 and minus 16 equivalent, converting very roughly from stellar mass with our model. I'll try and write you a better answer in the Slack, if that's all right.
Absolutely. Well, maybe one very last question from Kirsten. Nice and interesting talk. You said you consider a relatively simple description of the dust property, single size, solar chemical composition. How do you expect this affects your result if you had a more complex, complete dust description?
So I think, so again, it's very difficult to tell you without having done it. But so I think the main thing here is the resolution, right? I don't know how much more physics you can include without significantly increasing the resolution in the galaxies. At the moment, what we're aiming for is to have some effective dust population that has an effective impact on the photons we're dealing with. If we, without really starting to resolve the ISM, I'm not sure how far we can go, is my answer.
I also have another question, but I will ask it on the Slack because I think we are running short of time. So thank you, Joe, and thanks again. And let's move to the last speaker of this first session, who is Claudia Di Cesare. Claudia.
Hi.
Hi. So can you share your screen?
Yes.
And Claudia is going to tell us about the assembly of dusty galaxy redshift higher than 4 and so on. Thank you.
Okay. Just give me a second because of this. Okay. Okay, so hello everyone, and thanks to the organizers for giving me this opportunity. I'm Claudia Di Cesare, PhD student at Sapienza, University of Rome, and I work under the supervision of Professor Raffaella Schneider and Dr. Luca Graziani. Today, I will present you one of our latest work that is about the assembly of dusty galaxies at redshift higher than 4, with a particular focus on the scaling relations and the dusty environments of these galaxies. Okay, so it is a been while since we have observations of single high redshift dusty galaxies at the epoch of reionization. However, only recently, thanks to the high redshift surveys, such as the Alpine and Rebel surveys, we are able to build up a more comprehensive view of the high redshift galaxies evolution processes, and also on the early stages of the evolution of the scaling relations of these galaxies. So since these two surveys can be considered as complementary in redshift, and since they give us information, statistical information on these galaxies, we can use them to put some observational constraints on the scaling relations of the high redshift galaxies. These relations that are already observationally well established at lower redshift. So this is basically the main motivation behind this work. Of course, with JWST in the very near future, we will have more information and observations at this redshift. So I would like now to spend a few words on the model we adopted here in this work. That is, this model is Dusty Gadget. This code is Dusty Gadget, described in the paper by Graziani et al. 2020. Dusty Gadget is an extension of Gadget 2. And what it does is to run SPH hydrodynamical simulations with both POP3 and POP2 stellar populations. It follows the chemical evolution of the gas, and it also follows the dust production and evolution in both the hot and cold phase of the ISM. What is new in this work with respect to the previous one is that now we are using 8 statistically independent cosmic volumes, and that we now have a box size of 50 comoving megaparsec over H. So due to this, we are able to have an higher statistics and an higher mass resolution, so that we can probe the scaling relations at high redshift and also try to explore the high mass end of these relations. And what I need to say here is that there is a statistical convergence among these 8 cosmic volumes. So I will now go straight to some of the results. In this figure, you see the redshift evolution of the main sequence. So going from top left, redshift 10, we go down to bottom right, redshift 4. And so the gray dots are our simulated galaxies, while the purple solid line represents our best fit. And we compare our predictions with the observation by Rebels in blue, single observations collected in the paper by Graziani et al. 2020 in red, and at lower redshift, last 2 panels with the Alpine sample in orange and the observations by Santini et al. 2017 in black. So few comments on this for the pre-reionization epoch. First, for panel redshift higher than 6, you see how we do agree with the trend suggested by the Rebel survey. Of course, we have to take into account that there are large uncertainties on the stellar masses, so that we cannot really strong constrain this relation at this redshift. While for the lower redshift, we are consistent with the average trend constrained by both Alpine observations and single observations. So in general, we tend to agree, our prediction agree with the observations within the observational errors. What it is to be said, we have to bear in mind that that our best fit trend, it is heavily affected by the low mass objects with masses lower than 10 to the 9 solar masses. And that unfortunately, this part of the relation, it is the less constrained part. So we are waiting here for JWST for more results. And so I need to say that we didn't find any strong evolution, any evolution for the main sequence slope at this redshift consistently with the Alpine results. I do not have time to go into details for this, but I just want you to show the evolution, the redshift evolution of the specific star formation rate. So our prediction, our purple dots, do agree very well with the specific star formation trend, from Topping et al. 2022. That is the dashed black line. And so, okay, so I do not have time, but moving on the second scaling relation, here I show you the stellar mass function. The panel organization is the same as before. The pink solid line is our mean stellar mass function, while the pink shaded area represent our the statistical error associated with it. And once again, we compare our predictions with other models' predictions and observations. So for the top panels, you see how we do have a better agreement with the model by Beruzzi et al., so universe machine in red, compared to the one by Jung et al., by the model by Jung et al. 2019, that is dashed purple line. While we do have a general agreement with the observations within the observational errors. For the bottom panel, on the other hand, for the bottom panel, we have an agreement with both the other models predictions and observations for the high mass end of the relation, while we tend to predict more objects for the low mass end of the relation. That is once again the less constrained part of this relation. So in general, we do have an across the redshift agreement between our prediction, the observations, and other models for stellar masses higher than 10 to the 9 solar masses. Last but not least, the scaling the relation between the dust mass and the stellar mass. So the gray dots are once again our simulated galaxies. The panel organization is the same, and here we compare our predictions with Rebel, single observation, and Alpine sample, respectively in blue, red, and orange. So first thing, this new suite of simulations compared to the one by Graziani et al. 2020 do confirm this S-shaped trend that was already found in the previous work. And for the pre-reionization epoch, we do match some of the Rebels candidates, but once again, we have to bear in mind that there are large uncertainties, so we cannot really put a strong constraint on this part of the relation, on the high mass end. While at lower redshift, we do have a good agreement with the Alpine estimates and also with the ALS sample, that is the red dots. And so we can constrain the high mass end of the relation, but for the low mass end, it is at the moment unconstrained, observationally unconstrained. And so at this point, we ask ourselves if we can try to theoretically understand the spread of the dust mass at a fixed stellar masses at the low mass end. So In order to do so, we focus on the redshift range between 4 and 5, and we selected 4 galaxies in the black box across the spread in the dust mass at a fixed stellar mass. Okay, so here I have to say that this is a still in progress part of the work, so that I do not have strong conclusion on this at the moment. However, we are investigating the environments of these galaxies, and you will see, and by comparing the dust spatial distribution of the 2 extreme selected object, you see how the galaxy with the highest dust mass budget, so top 3 panels, seems to have a more compact structure. Yeah, okay, thank you. Seems to have a more compact structure, so it is more structure and there is a more diffuse dust compared to the galaxy at with the lowest dust mass budget, which has a more scattered structure, and the dust seems to be still clumped in the star-forming regions. Of course, this is just some preliminary and qualitative information on these galaxies. In fact, our next step is to have quantitative information, and so in order to have such information, we are analyzing the assembly histories of these galaxies, of these selected galaxies, in order to try to have some clues on the nature of this cluster. So if this could be a matter of feedback or any other physical process. So I'm basically done. So here are my conclusions. I will leave you with my conclusions, the work in progress, and also the planned future work. And thank you. And I'm happy to take questions, if any.
Thank you, Claudia, for staying in time and for the nice presentation. So any questions? I don't see for the moment on Slack or on. Sorry, I have some problems with my Windows. Maybe I have one, which is something which started to puzzle me also in the previous talk, that is, if you go to the evolution of the dust to gas, yes. Now it's difficult to assess here, but it seems that also in your case, if you compare the different redshifts, you don't have much evolution of the dust to stellar mass relation, which is a bit puzzling to me, because I would expect that as you start going below redshift 6 or 5, the AGB should kick in and change the relation. So do you have any idea why this?
Yeah, I mean, so we have this S-shaped trend, but yes, of course, we're not seeing such an evolution between these different, this relation at different redshift. So basically the AGB and supernovae contribution to the dust is given for the low mass sense. So at the beginning of this relation, so here basically, while as also Tom was saying before, for the high mass sense, we expect that also there are other processes contributing to the dust mass. But for the evolution, I just need to, yeah, at the moment, I do not have clues, yeah.
All right, thanks. Daniel has a question. Nice results. Do you see any trend between the dust ratio and star formation rate at fixed stellar mass?
Between the dust ratio, no, at the moment, I do not have this, but of course I can look at them and then answer on the, yeah, I do not have in mind these numbers. I can answer on Slack, yeah.
Good. Right, I don't think there are more questions. So I think since we are a bit behind the end of the session, I think we stop here. So thank you, Claudia. Thank you. All the speakers of these sessions. I don't know if the organizer have any communication before the break.
No, I think we just gather back in 15 minutes.
Okay, see you in 15 minutes then. Thanks.
Aniket, are you online?
Yes, I'm here.
Do you want to start sharing the screen?
Yep. Does that look good?
Yeah.
Okay.
I think we can wait until like 47
Yeah.
because we finished a bit late. And in any case, we have like 15 minutes for concluding remarks, which are mostly there for
Buffer zone.
Exactly, in case we go late.
Aniket, you might want to share also the video so that people see you.
Yep. Can you see me now?
Yes.
Okay.
So I guess we can start with the last session. So the first speaker is Aniket Bhagwat, and he will talk about co-spatial metal and 21 centimeter sorbers during the epoch of reionization.
Thank you so much. Hey everyone, I'm Aniket. I'm a PhD student at the Max Planck Institute for Astrophysics, and I'll be talking about co-spatial 21 centimeter and metal line absorbers. So this work was carried out in collaboration with Untitled Chapter, Zach Christen, and Joop Shea at Leiden. And I want to motivate using multiple techniques to study the high-redshift universe together. So studying galaxy and its environments, its connection to its environments is a very interesting question. And one of the main probes of studying this is using quasar absorption spectra. So I'm sure the first thing that you think of about the high-redshift universe when you think of quasar absorption spectra is the Lyman alpha forest. But unfortunately, the higher you go in redshift, getting information out of this becomes harder and harder because the Lyman alpha line saturates. But luckily for us, the grass is greener on the redwood side, where the metal absorption lines are. And metals indicate the local chemical enrichment, ionization states, etc. quite well, and can be very interesting probes of the high-redshift universe. Another excellent probe which has been used recently is the 21 centimeter line of neutral hydrogen. On the right here, you can see a simulated spectrum for a Cygnus A type source from a paper as early as 2002. And in the bottom, what I would like you to see is these two particular quantities here, which are the neutral hydrogen number density and temperature. So your 21 centimeter optical depth is determined by these two, and hence this line can act as a very good tracer of neutral hydrogen. Now, what I would like to do here is motivate the use of 21 centimeter with metal absorption lines together. So why does this matter? And here in the insets, I show you slices of a small region in a simulation that I've been using at redshift 7.5. And what you can see is these islands of very dense pockets, which have relatively high 21 centimeter optical depths, also neutral hydrogen number densities. So what could happen if these pockets of neutral gas survives all the way to the end of reionization, which is also metal rich, is that it can produce absorption in 21 centimeter as well as metals together. Now, what metals do we care about? So for this talk, I'll focus on these 4 particular absorption lines. In particular, oxygen 1, because of its ionization potential, it can exist in charge exchange equilibrium with hydrogen. So these specific lines are expected to be seen in neutral gas predominantly, and hence together these can act as pretty strong probes of gas at very high redshifts. So how do we go about this? I use the Aero Simulations run by Andreas Pavlik in 2016. The key is these also do radiation transport and track the neutral hydrogen fractions throughout reionization. And the plot here is exactly why we use this. You can see the dynamical range to resolve very small scale neutral pockets of gas within massively ionized regions. And this is important because these small pockets of neutral gas are exactly the target for our study. These simulations also track 11 metals, and obviously including the ones that we are interested in. So what we do is we use this publicly available code called Trident. We project sight lines through our simulation boxes in these 3 redshift bins, as I show here, calculate absorption spectra for all of our metal lines, as well as 21 centimeter, and use these to study, post-process these and study absorption from metals in 21 centimeter. Let's look at these sight lines for a moment here, and just plotting this visually, you will see a very nice evolution already. So the reionization process is eliminating the 21 centimeter forest progressively through redshift. And as Christian mentioned earlier in his talk, that it's always a competition between metal enrichment and reionization. So this produces some very interesting scenarios where metals predominantly show up in transmission windows of 21 centimeter, but there are also cases, as you can see from this particular absorber here, this particular absorber here, etc., where a lot of these absorption lines just are aligned in a sense. So when you plot them together, they do appear within the same velocity windows and could potentially originate from the same underlying gas. So how do we study this? We find these absorbing windows, what we call aligned absorbing windows. And it's essentially a velocity window where we have absorption from at least 1 metal of interest and 21 centimeter, because the goal is to study these together. And we calculate these spectra with peculiar velocity effects and without peculiar velocity effects. Now, the question is, you would think these come from the same underlying structure. Is this the truth? What we find is, I would like you to focus on the plots here. On the left side, in the middle panel, when the peculiar velocities are turned off, you see metal absorbers, but they do not align with the 21 centimeter forest. In the lower panel, when you turn on the peculiar velocity effects, they do appear to be aligned. And on the right side, they are, with or without peculiar velocities, they still appear aligned. Now, obviously, observers do not have information without the peculiar velocities. So the question is, how do we differentiate between these two? This apparent alignment, which is caused by peculiar velocity effects. So we use 3 particular quantities. One of them is the integrated equivalent width within a given window. The second one is the number of pixels that show 21 centimeter absorption. So if you look at this, the lower left panel, you see that a significant portion of the absorbing window shows 21 centimeter absorption, whereas on the right, it's a very small isolated portion of the spectrum. And the strength of the 21 centimeter absorption within a window. So again, if you look on the left, the 21 centimeter absorption is quite strong, whereas on the right, it's relatively weaker as compared to the left. So using these two, we define 2 distinct categories, aligned and co-spatial. So for example, the one on the right, where the absorption originates from the same underlying gas and traces this large-scale structure that lives underneath this absorption feature. And aligned but not co-spatial, which is an artifact because of peculiar velocity effects, where it might look like it's aligned, but it's not. So does this classifying pipeline that we use here, does it work? And this is essentially what I would like you to take away from this talk is if you find these windows and classify using the three criteria that we see, the two kinds of absorbers separate themselves in very distinct corners of the equivalent with phase space. On the right-hand side are the aligned but not co-spatial ones, which are produced by peculiar velocity effects. And on the left, indicated by the stars, are the legitimately aligned and co-spatial absorbers. And so the stars are particularly good at tracing underlying structure, and the circles are just artifacts. And hence, using this section, we can separate these and essentially classify these quite successfully. One very interesting thing that you can see from this plot as well is there is very strong redshift evolution, where the contaminants or the aligned but not co-spatial absorbers dominate at very high redshifts, and they evolve and completely disappear by the end of reionization, whereas the aligned and co-spatial absorbers increase their incidence as you go down the redshift. And this is essentially just more and more metals being produced, and the neutral hydrogen mostly being confined to very small, dense pockets by the end of reionization. So the peculiar velocities have the same effect on both 21 centimeter and metals, since they originate from the same underlying gas. Now, here we've shown that these absorbers exist. They are very special cases, but the question is, can we observe this and get information out of this about the underlying gas properties? So to study this, we want to make mock observations for the next generation of telescopes. And for this particular study, we look at the ELT and the SKA, which hopefully we have observing in the next few years. So to simulate this, we assume a background quasar at redshift 8. Thank you. So we assume a background quasar at redshift 8 with a AV magnitude of 21, which is also radio loud and has a radio continuum flux of 10 millijansky. So for the ELT part, our collaborator Eric Zacharyson produced the mocks for us using a 10-hour exposure and calculated the signal to noise and produce a spectra. For the SKA simulated spectra, I use this tool called OSCAR, produce the interferometric data, produce the data cubes, assuming full coverage as shown in this plot here. And basically we overlay these into our mock observations, and this is what this looks like. Now this is a loaded plot. I'll quickly take you through it. The top panel are the noiseless synthetic spectra that we make. In the middle here is the simulated ELT spectrum with noise and sky transmission. In the bottom is the simulated SKA spectrum, and on the left, we zoom in on the absorbing window of interest, where we expect these aligned and co-spatial absorbers to exist. And the panel D here is just the middle one and the left one overlaid with each other on in velocity space. So we do find a detection of a relatively weak oxygen 1 line with 21 centimeter using this reasonably bright quasar at redshift 8. And so to sum it up, I'll leave you with my summary. What we are also working on at the moment is connecting these populations of absorbers to underlying galaxy properties to see if these particularly trace certain environments, certain galaxies, and now also use, because we have multiple lines, we can use the ratios, etc., to produce quantitative constraints on gas properties. Also, one of my favorite XKCD comics. Thank you. And I'll take questions.
Thank you, Aniket. We have a question from Valentina. Very interesting talk. I think I've missed how you model the ionization state of the gas.
Yes. So for hydrogen, we have on-the-fly radiative transfer. So the ionization states of hydrogen are tracked within the simulation as a result of the radiative transfer. We use those. For the metals, doing metal radiative transfer is obviously difficult. So instead, we assume a local Hartmut 2012 UV background and then calculate the ionization states using that.
We have another question from Christian. It's helpful to be aware of the ACA, ANCA distinction. Is there a way to distinguish between them observationally?
Yes. So, well, you will need the 21 centimeter observations together. And I think observationally as well, as long as you find these simultaneous detections using equivalent width and these fraction of window with 21 centimeter absorbers cuts, you should be able to reliably distinguish between those two. Yeah, and that was one of the main points that we would like to make here.
We have time for a last question from Enrico.
Yeah, nice work, Annika. Maybe I missed it, but so it seems that the way you distinguish between these two type of absorbers depends on the observing windows you choose. And so I was wondering, how do you choose it, and if you know how?
Yes, so the observing window is calculated. So I've done this test where instead of observing windows are calculated using a flux decrement technique, which is the usual detection routine. What I have also done is convolve this with Gaussians of different full width half maximums. So you can get very, very well constrained observing windows as opposed to very, very massive and extended absorbing windows. And across this, the results still converge very well. I hope I've answered your question. If not, please.
Yeah, thank you.
Okay.
So Valentina has a side note for the next time you give the talk, that the high resolution spectrograph of the ELT is now called Andes. So
Andes, okay, thank you.
And so if you have, there are a few more comments on Slack, so please go there.
I will answer them.
And have a look at those. Thank you very much. Then we can move to the next speaker, Antonello Calabro, probing chemical and dust evolution at high redshift with bundles.
Yes, can you see it?
Yes, thank you. Please go ahead.
Okay. So I am Antonello Calabro from the Observatory of Rome. First of all, I would like to thank the organizers for giving me this opportunity. So given the general topic of this SAZERAC session, I would like to present my work about chemical enrichment in high redshift galaxies. The motivation of my work from a broad astrophysical view is that we are interested to understand how and when the first metals were produced by the stars and how they were spread inside the interstellar medium of galaxies and in the circumgalactic medium. So of course, the chemical enrichment history is tightly related to the history of star formation. And so we expect a gradual increase of metallicity as a function of time, as it is indeed observed up to at least a redshift of 3 or 3.5, as you can see in the bottom right plot. But in order to better characterize the chemical enrichment history from a statistical point of view, we can look at the so-called mass metallicity relation, which is the relation between the stellar mass and both gas phase and stellar metallicity that is well studied in the local universe, as you see in these two figures. Regarding the gas phase metallicity, there are several studies showing that a similar relation was in place also at higher redshift, at least up to redshift 3.5, as shown by Maiolin et al. 2008. With a strong evolution of about 1 order of magnitude between redshift 0 and 3.5. But so the goal of my work was to understand instead the evolution of the stellar phase metallicity relation, which is more difficult to characterize because it is based on absorption lines instead of emission lines, and so it requires deep spectra with high signal to noise stellar continua. But why are we interested in the stellar metallicity? So, well, apart from the fact that it traces an additional, still important component of galaxies, it also traces a different time scale of chemical enrichment. Indeed, as you can see in this bottom right plot, while the gas phase metallicity traces the oxygen abundance, where the oxygen is released mainly on short time scales after the onset of star formation by core collapse supernovae. This is the red curve. On the other hand, the stellar metallicity traces the iron abundance, because the iron is the element that contributes the most to the opacity of the stellar atmospheres, but this element is released on longer time scales, mainly by type 1a supernovae. So look at the blue curve. So this might produce an offset between these two estimates. And this offset, of course, depends also on the past history of star formation of the galaxies. So in this study, I will derive the stellar metallicity from Vandel's spectra. So why Vandel's? The reason is that Vandel's is so far the deepest spectroscopic survey, targeting more than 1,000 star-forming galaxies in the redshift range between 2 and 5, as you can see from the redshift distribution. And these are mainly normal star-forming galaxies belonging to the main sequence of star formation. And each target was observed for 20 up to 80 hours, reaching very high signal-to-noise spectra of at least 7 for 80% of the sources. So we tried to push these to more hours of integration in order to facilitate the measurements of absorption lines. And you can find all the details of this survey in this last paper, which also presents the final public catalog published in 2021 by Garilli and collaborators. But how are the metallicity, stellar metallicity derived from the spectra? So this is a representative stack of more than 100 galaxies in bundles that shows you the spectral range that is covered by the survey. And you can see also plenty of features both in emission and in absorption. And most of the absorption lines, in particular the deepest ones, are arising in the ISM. But we are interested in faint photospheric lines that are able to trace instead the stellar metallicity. And so I did several tests with the BBUS and Starbus 99 models, and I found that these two features highlighted in yellow and located around 1501 angstrom, which is mainly produced by the sulfur 5 element, and the other one located around 1719 angstrom, which is instead a blend of different chemical elements. They are genuine tracers of the stellar metallicity because they do not depend on variations of the stellar age, IMF, dust attenuation, and they are also not significantly contaminated by ISM absorption. So I would like to remark that these two features are the only good metallicity and reliable metallicity tracers in this far UV spectral range, given the resolution of Vandel's, which is around 600, because all the other features that I studied, they either do not correlate at all with the stellar metallicity, or they are more contaminated by the ISM absorption. And so in this paper published in 2021, you can find the calibrations from which you can convert the observed equivalent width of the two indices into a stellar metallicity using Starbus 99 models, but there are similar calibrations also for BPAS models. Interestingly, comparing the equivalent width of the two indices, they are consistent with the model predictions, as shown here. So this means that you can also apply separately a metallicity estimate from each of the two indices, and these two estimates are consistent within each other. So at the end, we can take the median as a final value in order to increase even more the signal to noise. And it's important to say also that we can do this measurement on spectral stacks, because as found from simulations, in order to get uncertainties on the stellar metallicity by 0.1 dex or lower, we need a signal-to-noise ratio on the stellar continuum higher than 20 on average, which is impossible to get for individual galaxies alone. I will also mention, since I will talk about also dust attenuation later, that for all bundled galaxies, I also computed the so-called UV slope from the available photometry in the candles fields and also in the wider CDFS and UDFS fields covered by the bundled survey. And this is the UV slope stellar mass relation. You can see on the left y-axis the attenuation at 1600 angstrom. Indeed, the UV slope is used as a proxy for the dust attenuation. Once you assume an attenuation law, in this case is a Calzetti attenuation law that was used for the conversion between beta and A1600. So we go to the results. So first we investigated the stellar mass-stellar metallicity relation in the redshift range between 2 and 5, which is shown here with the black squares. And here we found a steep increase of stellar metallicity of about 0.5 dex in the stellar mass range between 10 to the 9 and 10 to the 10.5 solar masses. You can find the best fit linear relation here and also in the paper. Then we also divided the sample into redshift bins below and above 3. So here I forgot to mention that we are using approximately 800 galaxies in total, that are those which have a reliable estimate of the spectroscopic redshift in order to perform a good stack. So here we do not find a significant evolution in redshift of this relation between the two redshift bins if we look at the blue and the red squares. But of course there is a large offset if we compare this relation to the local one measured from the Sloan galaxies. As a note of caution, we have to take in mind that so in the local relation was estimated using slightly different absorption lines in the optical rays frame, so they might trace slightly more evolved stellar populations. And then we can also compare the stellar metallicity to the gas phase metallicity, as I was mentioning before in the introduction. So I contributed to a paper that was published last year in the Bandes collaboration, where we derived the gas phase metallicity for a subset of 33 galaxies, which were followed up with MOSFIRE. And we found that the gas phase metallicity, represented with these two red triangles, is about 0.2 dex higher compared to the stellar metallicity. This means that we have an alpha enhancement, oxygen over iron, which is well above unity of approximately 2.5. And this is an indication that we are witnessing an early phase of galaxy evolution where the galaxies didn't have time to produce much iron, at least to reach the solar level. Then we can compare also the observations to the predictions of theoretical models. So in this plot on the right, I compare the Bandes observed data with the predictions of the Gaia semianalytic model, represented with these orange diamonds, and with the semianalytic model by Mensch et al. 2002. Which is this blue shaded region. And remarkably, the models are well able to reproduce the observed slope of the relation. So this means that we have a good understanding, at least, of the basic physical processes that are able to shape this relation. But there is still a normalization offset problem, which might be due to several factors, including the chemical treatment of the models, or even the way the metallicity is weighted in the models itself. Then here I show instead that the stellar metallicity can be used to explain a part of the scatter of the UV magnitude beta slope and the stellar mass beta slope relations. So here the big stars represent the spectra stacks that I made in 4 bin for each diagram. And a lighter red indicates a lower stellar metallicity of the stack. So in particular, in the bottom diagram, we can see that there is not only a strong relation between stellar mass and stellar metallicity, but there is also a variation of metallicity in the vertical direction as a function of the UV slope, or let's say of the dust attenuation. So the two quantities are well correlated, and we can directly study one against the other, and this is what I have done here. So here I constructed the 3 bins of increasing the UV slope, and for each bin I derived the stellar metallicity, and we can see that the relation that we get is reassuring in the sense that it's consistent with the relation that is obtained by combining the mass metallicity relation that I showed before and the best fit stellar mass beta relation. So of course, in the future, we will be interested to study the bottom left part of this diagram, trying to understand the dust attenuation properties also of earlier galaxies, which are thought to be more metal poor. So I would like to conclude by highlighting the main conclusions. So we studied and characterized the redshift evolution of the stellar mass-stellar metallicity relation. So we find that such a relation is still in place also at redshift 3. And finally, we have also seen how the stellar metallicity is related to other physical properties of the galaxies, like the UV slope or the dust attenuation. So it is really a useful quantity to constrain other properties. So I will be happy to take questions, and thanks for the attention.
Thank you, Antonello. We have time only for one quick question. I don't see any, so let me ask, I have a curiosity. So at a certain point you said that you were using the Bruce-Wallen-Charlot model for the spectral energy distribution. So from the point of view of reionization, we see that if you use different spectral energy distribution, for example, from BPAS, including binary stars, this makes a big difference. So would for you the adoption of a different spectral energy distribution make any difference for the final outcome, or this doesn't have any impact?
So the effect of using the BPAS models, so we can still use these two features as a metallicity tracers. But the calibration is slightly different, and at the end we obtain an offset of about 0.1 dex, but the slope of the stellar mass-stellar metallicity relation remains the same. We only get a slightly lower stellar metallicity if we use BPAS models. But well, we can also derive stellar metallicity based on a different assumption of the models, like it is done in some recent bundles publications.
Okay, thank you. Then we need to move to the next speaker, and the exchange can continue on Slack. Clearly, you can start also typing your questions on Slack while the talk is given. You don't need to wait until the end. So the next speaker is Laura Somovigo on the obscure puzzle of EOR galaxies.
Hi, so let me show my screen. Okay, do you see my slides in full screen mode?
Yeah.
Okay, perfect. So I'm going to start. Okay, so hi everybody, I'm Laura Somovigo and I'm now finishing my PhD at Scuola Normale Superiore where I've been mainly working with Professor Andrea Ferrara, producing models for dust obscuration in epoch of reionization galaxies. So since this is a very specialized audience, I'm going to skip my usual introduction and just mention very quickly what is the main observational challenge that we face when studying the dust emission for very high redshift galaxies. Here you see the spectra of a low redshift galaxy at redshift 2, whereas here you see the spectra of a redshift 6 galaxy. So you can see that for the low redshift galaxy, we have a lot of data points that really trace the dust continuum emission, so the far infrared SED, at all wavelengths on both sides of the far infrared emission peak. On the other hand, for high redshift galaxies, the only available instrument is ALMA, and it only traces the very long wavelength side of the infrared spectra. Particularly, the most commonly used ALMA bands 6 and 7 trace an area where it's very hard to discriminate between different gray body curves corresponding to different dust temperatures and dust masses. And more often than not, and this is the case of large programs such as Alpine and Rebels that I'm going to discuss in a few slides, a single continuum data point is available for the individual observed sources. This means that we cannot constrain the infrared SED shape of high redshift galaxies, nor can we constrain their dust temperature. So what people generally do is to assume a value for the dust temperature to then derive all the dependent properties of high redshift galaxies. However, this casts large uncertainties on several very important high redshift galaxies properties, for instance, the dust mass. And so we are also not really able to constrain what are the dust production mechanisms at play at the early universe, although obviously we have some good guesses. On the other hand, since we don't really know what is the infrared luminosity of these sources due to the uncertainty on the dust temperature, we also don't know the obscured fraction of the star formation rate in these high redshift galaxies. And you understand that this is a particularly important question when we're speaking of the sources that are likely responsible for the reionization of the universe, for which we really want to know their total intrinsic star formation rate. So what people have been trying to do to work around this observational issue is to study stacked data. Stacked data basically allow you to access the spectra of galaxies which are too faint to be detected individually. And what they have been finding is very interesting because they suggest that there is a tight correlation between the dust temperature obtained from the fitting of these stacked SEDs and redshift of the sources considered in the stacking. These results here are from Schreiber's work of 2018, and then you see the results from the Alpine collaboration at redshift 4 to 6. So what people have been doing after that is to add the few sources for which we have dust temperature estimates individually at redshift higher than 5 and try to understand whether this correlation is still there even at the epoch of reionization. And what is interesting and puzzling is that different works have arrived to pretty different conclusions, with these results being the latest ones by Aero, also mentioned in Tom's talk. And what has really been hindering the progress in this matter is the fact that at the very high redshift end, where the discrepancy between these different fitting relations is larger, we have very few data. And the few ones that we have are affected by very, very large uncertainties. But on top of all of that, there's a bigger issue, which is the fact that all of these trends that I'm showing here are based on fits to either data or simulations in the case of Liang's work, but they do not rely on a physical modeling, which means that we don't really understand why there should be a cosmic dust temperature evolution in the first place. At least for the lack of sources at the high redshift end, the recent ALMA large program Rebels can help us progress further. Just a few words on Rebels for who among you don't know it. It's Rebels is an ALMA large program which targeted 40 of the UV brightest sources between redshift 6.5 and 9.5. And you can find more details in the flagship paper by Richard Bowens, who is the PI of the program. But basically, we've been scanning for the C2 NO3 line emission and the underlying dust continuum. So what is important for the sakes of this talk is that Rebel provided us with the first statistical sample of redshift 7 for infrared continuum detected galaxies. However, these groundbreaking data come with a drawback, which I was mentioning in the first slide, which is the fact that we only have a single continuum data for the individual Rebel sources, meaning that with traditional SED fitting, we're not really able to do much with this really interesting data. With this problem in mind, in my paper of 2021, we proposed a new method to derive the dust temperature and the dust mass by combining the continuum information with the overlying C2 information, which is obtained for free in most cases whenever you're looking at 158 micron continuum. Or actually, people target the C2 and get the dust continuum for free. So our simple idea was to rewrite the dust mass as a product of a dust-to-gas ratio, which we consider to scale linearly with the metallicity, and a C2 to total gas conversion factor, this alpha C2, which we then multiply by the C2 luminosity to obtain the dust mass. We use well-known empirical relations to obtain an analytical formula for this alpha C2, which are the Deleuze relation connecting the C2 luminosity and the star formation rate, and the Kennigat-Smith relation. So let me say this again in brief. Basically, with one single band observation, we are able to constrain multiple dust properties and, in the end, the whole infrared SCD, because we use the C2 luminosity as a proxy for the dust mass, and then the underlying continuum to constrain the dust temperature. This method has been tested on several local and high-redshift galaxies, and actually also on simulations. And in all cases, we recover the same dust temperature that we would obtain with traditional SCD fitting, relying on multiple infrared data points. And this is shown here in this plot. Among all these sources, I want to spend a few words on one in particular, which is the Galaxies 81, which was presented by Tom in his talk. And what is interesting is that even in this galaxy, where we have the best constraints on the dust temperature and the SCD shape for such a high-redshift galaxy, thanks to ALMA Ben 9 data, we were actually right to begin with our guess based on the 158 micron observations, although obviously our uncertainty was much larger. So let me now introduce you to our Rebels C2 and continuum detected sources. Here you are seeing the continuum and C2 maps that you can find in Hannah Inami's paper. And these are the SCDs that we predict for these sources, which are color-coded according to the predicted dust temperature. Let me summarize the results. We find that for Rebels galaxies, the dust temperatures vary in the range between basically 40 and 60 Kelvin, and the dust masses are in a very narrow range around 10 to the 7 solar masses. So knowing the dust masses of these sources and their stellar masses, we can actually constrain what is the dust yield that is needed to produce the inferred dust masses in each supernovae event. And we find that it is below 1 solar mass per each supernovae explosion, which is consistent with dust production constraints from supernovae. But we can do something more, and we can compare the dust versus stellar mass relation that we find in Rebels galaxies with semi-analytical models. And this is actually done in detail in Pratica Varial's paper of 2022. So what you see here are the Rebels data points and the predictions from different models, where the solid lines are the fiducial predictions, whereas the dashed lines are the maximal predictions, where you are really assuming an unphysical scenario where no dust is destroyed and you have saturated grain growth. And you can see that in most cases, we're actually consistent with theoretical models, but there are a couple of puzzles that arise from this plot. So here I've added, just in passing, the weirdest source that Joris was showing us in his previous talk. And you can see that this adds up to the Rebels galaxies, the outliers Rebels galaxies. These are galaxies with the lowest stellar masses in the sample, below 10 to the 9.5. And weirdly enough, they appear to have a very similar dust mass with respect to the more massive sources in the sample.
3 minutes.
Yes, thanks. So this would imply that there is a really flat relation between the dust and the stellar mass relation at redshift 7, which is kind of not consistent with what we expect in terms of the mass metallicity relation. What I've been doing lately is to apply my same method to the alpine galaxies and add them in this plot. And interestingly enough, in this case, for the alpine sample, which samples a larger range of stellar masses, we actually recover the slope that we expect from theoretical models. So this might hint two things: either that that these Rebels outliers are really weird sources, or if this flat slope at redshift 7 is actually confirmed by other observations, that we are seeing an evolution in the mass metallicity relation from redshift 5 to redshift 7. So very quickly, let me conclude with the cosmic dust temperature evolution results. So the first thing, what we can do with our method is to uniquely compare individual sources from low to high redshift, and this is what is shown here. Here you have the individual sources that were stacked in Schreiber's work of 2018. Here are the our results for the Alpine sources, and here are the Rebel sources. And then you have the few other galaxies that are observed at such high redshift. All these dust temperatures are obtained in a consistent way with my method, but we have also compared whenever they are available with the estimates from traditional SAD fitting, checking that we are consistent. At this point, we could have closed the deal by doing a fit of these data points, but we wanted to address the other pressing issues, so the lack of a physical motivation for a cosmic dust temperature evolution. Now, I don't have time to enter in the details of the model, but basically, the main point is that we find that the dust temperature anti-correlates with the total gas depletion time in galaxies, which is the ratio between the total gas mass and the star formation rate. And we know that this quantity is redshift dependent. In fact, higher redshift galaxies have lower total gas depletion times. So this in turn means that the dust temperature raises with redshift due to the decreasing gas depletion time at earlier epochs. This is the prediction from our model, and you can see that it's pretty much consistent with the data. We find a mild redshift evolution as 1 plus e to the 0.42. But you can also see that there is an additional term in our equation which depends on individual galaxy properties, namely the UV optical depth, tau UV, and metallicity. By considering a range of values for these two parameters, we can actually explain the scatter in the dust temperature which are measured at a given redshift or in a narrow redshift range. So we can color an area in this TD versus redshift plot. We're moving from bottom to top, so from colder temperatures to hotter temperatures. We are moving from more UV transparent galaxies to more UV obscured galaxies. So basically what we are saying is that in general, galaxies which are more UV obscure tend to also host hotter dust. And this is qualitatively confirmed by sub-millimeter galaxies observations, which generally tend to show dust temperatures which are warmer with respect to the UV bright galaxies at the same redshift. I'm going to leave it my conclusions. I don't think I have the time to sketch them, but I'm happy to take any questions also offline. Thanks.
Thank you, Laura, for a very nice talk. I really liked your last slide with the temperature of the dust. And Christian actually writes beautiful work and gorgeous slides.
Thanks.
He agrees with me. So apart from this comment on Slack, there is no question, but there is, hold on a second, something in the chat here. No, sorry, it was your question.
Yeah, sorry, my question for Antonello.
There is one from Joris. Great talk, Laura. Do you think stellar masses could be underestimated for the low mass end to explain the flattening of the relation between stellar and dust mass?
Yes, so let me go back to this slide. I actually wanted to mention this, but then I was short on time. So for these stellar masses, for these galaxies here in the Rebel sample, we are actually suggesting that this might be the case. And this is shown in Michael Topping's paper of this same year from the Rebels collaboration, where he shows that if we apply a different SAD fitting to the optical to near infrared data, not assuming a constant star formation rate history, but rather a more bursty one, we actually predict much larger stellar masses for these sources, which would bring them more like closer to the other points and more consistent with theoretical predictions. So that's a possibility. I don't know what kind of fitting you were applying to your source, Joris, so I cannot say anything for that, but I'm sure you know it better and we can actually chat afterwards because I'm really interested.
Are there other quick questions? I have a curiosity, but maybe I'll just write it on Slack because we are approaching the end of the time. So we'll do that on offline. Thank you very much again for your nice talk. So let's move to the last speaker of the day, Andrea Saccardi, shedding light on galaxies at the end of the reionization epoch with long gamma ray bursts.
Okay, we see the presentation. You see the presentation?
Yeah.
Perfect. Thank you very much, Benedetta, and also Valentina and Enrico for this conference and for giving me the possibility to show the recent results of my work. I am Andrea Saccardi, first year PhD student at the Observatoire de Paris at GP under the supervision of Susanna Vergani. And today I will show you the results concerning the host galaxy of GRB 210905A at redshift 6.3. So let's start with the major issues of extragalactic astronomy. The main questions are: what are the first objects to be formed in the universe? What is the impact on the reionization? And what is the interplay between first stars, first galaxies, and the interstellar gas? According to the cosmological lambda CDM model, the formation of the first astrophysical object happened around 200 million years after the Big Bang at redshift 20. They decreed the end of the so-called dark age, since they are the first source of photon which ionize hydrogen and of the first chemical element heavier than hydrogen and helium. So they transform the universe from its initial state of simplicity, so-called zero metallicity, into one of increasing complexity. So understanding their role is crucial, above all from the point of view of the chemical enrichment of the universe. So in order to answer to this question, the main goal is to look for the signature of first stars and first galaxies. An amazing and promising tool to unveil the chemical properties of the high-redshift universe are gamma ray bursts. An ultra-relativistic jet produced by a newborn accreting black hole. They are characterized by a prompt emission detectable in gamma ray and followed by a bright afterglow emission detectable at all the frequencies that is due to the shock between the jet and the interstellar medium. They are divided into two classes: short gamma ray bursts that are linked with the merger of two compact objects, and long gamma ray bursts that are associated with the collapse of a massive stars. Thanks to the brightness of the afterglow, we can study the properties of the gas in the interstellar medium, without which we can't make the same kind of study with the current instrument, also the best that we have. And thanks to the brightness of the afterglow, also we can study the formation and evolution of faint star-forming galaxy, not selected by luminosity as in galaxy survey. So I want to focus the attention on long gamma ray bursts, since they are unique, powerful background source to probe the first galaxies. Why? Because the radiation emitted by the afterglow of the GRB travel along the line of sight up to telescope ground-based, and we are able to follow up the detection of the GRB and obtain absorption spectrum, not only of the intervening system as we do with quasars, but also of the host galaxy of the GRB. I show you here an example of absorption spectrum. We see the Lyman alpha in absorption of the Lyman alpha of the host galaxy. In absorption, we see the Lyman alpha forest, so the absorption due to the intergalactic medium, the Lyman limit, and on the red side of the spectrum, at longer wavelength respect to the Lyman alpha of the host, we see the absorption lines due to the metals. So from the analysis of this spectrum, you can measure the redshift of the absorbers and the column density of the ions of different chemical elements. I show you now the amazing X-shooter spectrum that we have for the host galaxy at redshift 6. We see the low ionization lines, the fine structure lines, and the ionization lines. We fit all the components. We see that it's a very complex system in velocity structure. We see two big clamps, A and B. Each clamp has 3 components, so for a total of 6 components. From the fit of these absorption lines, we studied the metallicity and the dust depletion of the galaxy. We calculate the distance of the corresponding gas cloud from the fine structure line. So we determine the distance of the closest low ionization clouds. We discuss the kinematic of the gas, and finally we obtain and try to interpret the chemical abundance pattern. So in detail, we perform analysis on metallicity, chemical enrichment, and dust depletion, as shown yesterday by Annalisa on behalf of Tanita. I briefly re-explain this plot. On X, we have the in quantity that give us the information of how refractory is an element, while on Y there is the element abundances. And if the fit is horizontal, it means that there is no dust depletion, while if the fit has a slope different from 0, this gives us the amount of dust that there is in the overall of galaxy. Indeed, the slope is zinc over iron, while the intercept at x equal to 0 give us the total metallicity. We took into account also alpha element enhancement, since at redshift 6, like 1 gigayear after the Big Bang, it is reasonable to think that supernova type 1a didn't have time to explode and contaminate the surrounding gas with other elements. So we performed also the analysis component by component, so for all the 6 components, and we see that 4 components has no dust depletion, while component 2 and component 6 has an amount of dust different from 0. And component 2 and component 6 are also the strongest in the spectrum, and they have also fine structure lines. So I show you the results. I show you the total metallicity and the dust to metal ratio, the evolution with redshift of the Milky Way in red, quasar DLA in orange, and GRB in blue. But I don't want to speak about the slope or the evolution with redshift, but I want only to focus the attention on the fact that through gamma ray burst, we can reach very high redshift universe. This is why we need high redshift detection of GRB to increase the statistic and to make the same kind of analysis that I showed you before. Then we determine the abundance pattern for each component. So the deviation from the linear fit that I showed you before, after the correction for dust depletion and alpha element enhancement, the deviation from the fit give us the X over iron due only to nucleosynthesis. So we show here the abundance pattern of each component, and we see that there is a high enhancement in alpha elements. For example, component 3, which is the one with the greater number of measurement, we see a high enhancement in alpha element, and probably this can indicate an higher production of this element from core collapse supernovae and can indicate a higher fraction of massive star. We see also an overabundance of aluminum, component 2, component 3, and component 4. It is the second time that we already found this enhancement, overabundance of aluminum at a high redshift. And also we see an underabundance of oxygen in some components. But anyway, this kind of abundance pattern are also typical of some stars in globular clusters and dwarf galaxies. And the best candidate that can explain this kind of abundance pattern are massive AGB stars and fast rotating massive stars. So here a sketch to recap all the information that we have from the analysis, the dust to metal ratio, so the dust depletion, the velocity structure, the distances of the corresponding gas cloud. So in order to try to understand the kinematics of this complex system, different scenarios can explain these, like if we are looking at the results of the merger of 2 galaxies, more clamps, so a clumpy environment, or more galaxies if the GRB explode in a galaxy near to the one that we are looking at. So in order to disentangle different kind of scenarios of this complex system, we need more data from VLT-MUSE, JWST, HST, in order to link the properties of the neutral warm gas, so the information from the absorption line that we already have, with the continuum and the ionized gas from the emission line. I want to say that the HST proposal was accepted and observed like 2 weeks ago. We have here the image in this filter, and it confirms that there is a complex system at like a clumpy environment near to the afterglow position. So in order to make this kind of analysis and to obtain this kind of results, we need a greater number of high-redshift GRB. And so to cover this region, yellow region populated by high-redshift gamma-ray burst, we need new instrument with a lower energy range that is not covered by the current satellite that we have. So we have two new missions. That is, one is Theseus, that is European, and the other is Gamma Explorer, that is American. I want to speak about Theseus. That is, it was pre-selected in M5 call with another mission that was selected, and yet it was Envision, and now is reproposed at the M7 call of ESA. I show you as a recap of some main goal concerning the exploration of the universe with gamma-ray bursts, but I want to focus the attention on the payload, to the fact that there is a soft X-ray imager that gives us the possibility to detect a larger number of high-redshift GRB. And the novelty, the real novelty, is the infrared telescope that gives us the possibility to determine like between 40 and 80 new GRB at redshift greater than 6 in 4 years mission of Theseus. Here the operation sequence after the trigger. So briefly, after the trigger, the ERT telescope will enter in the follow-up mode, and it will give the position of the GRB, the photometric redshift. So we will be able to pre-select the high redshift GRB, and after it will enter in the characterization mode. And depending on the brightness of the source, it will acquire a spectrum or multi-filter deep imaging. So this information will be sent to ground for analysis, and we will be able to follow up the detection of this high redshift GRB with telescope ground-based like VLT and in the future ELT. So I hope that I convince you the fact that with long gamma ray bars we can make amazing study at high redshift. So we need this telescope in order to have more data at high redshift. Thanks for the attention.
Thank you, Andrea, for a very nice talk. I'm actually a big fan of gamma ray bursts. They're not as biased with tracers as quasars are. So let's see if there are. Okay, Valentina has a question. Very interesting and nice talk. I have missed the H1 column density of your system.
Yes, Valentina. The column is 21.1. And there is also a companion paper respect to the fitting of the hydrogen, neutral hydrogen in the spectrum.
I have a curiosity myself, as I'm not following the literature as much as other fields. So of the few high redshift gamma ray bursts, is this the only one that has this amazing follow-up data, or
no? Like this, we have only 2 GRB that give us the possibility to make this kind of analysis to determine the total metallicity and the dust to metal ratio, obtain all the chemical information about the absorption lines.
And which redshifts are these?
This is the one that I showed before is a redshift 6.3, and the other are redshift 5.9.
Okay, so that's the highest. That's the one.
Yes.
One, yeah. But this is the same one. Okay, yeah. Sorry, I don't remember. It's Cherno, something like that. It doesn't matter. I'll check by myself. Are there more questions for Andrea? If not, thank you again for the nice talk, and thanks to all the speakers of the last session and of yesterday and today. I thought this was a really nice SIP, and we were missing something focused on high redshift metals and dust. Enrico, do you want to say, Valentina, some last words?
I want just to join you in thanking everyone for making this happening, and this includes the people that work behind the the screen in this case, in the LOC, like Andrea, Aniket, and Argyadip, and yeah, all the speakers, of course, for contributing to this.
Yeah, maybe we can clap for everyone.
Sure.
For these 2 days. And yeah, it was really very, very interesting, very nice results, and both observationally and theoretically.
Yeah, and let's just maybe close, hoping to see each other in person soon, as soon as possible, as soon as the situation allows. Yeah, so I would say thanks everyone, and hopefully see you soon in one way or the other.
Thank you.
Bye. 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 Bye.
Bye.